Welcome to the next chapter of the Modular Monolith Architecture course. In this chapter, we will be talking about reliable messaging in a modular monolith, and I'm going to introduce you to the outbox and inbox patterns that will help us build a reliable messaging system. This is our high-level plan for this chapter, and I want to kick things off with a discussion about asynchronous messaging guarantees. Then we are going to continue our discussion by introducing the outbox and inbox patterns. I'm going to explain why these patterns are useful, and of course I'm going to show you how we are going to implement them into the modular monolith architecture. And last but definitely not least, we are going to talk about idempotency when it comes to messaging and how idempotency fits into the outbox and inbox patterns. Here's a quick reminder of the fallacies of distributed computing that we mentioned in one of the previous chapters. And the fallacies are: the network is reliable, latency is zero, bandwidth is infinite, the network is secure, topology doesn't change, there is one administrator, transport cost is zero, and the network is homogeneous. And the reason I'm bringing up the fallacies of distributed computing again is because they are important when it comes to asynchronous messaging. In any kind of messaging system, there is always the possibility that a message could get lost and not reach its destination, which means that the message broker will not get an acknowledgement back. And this is going to cause the message broker to potentially deliver the message again, which could lead to receiving the same message more than once inside of a consumer. There are three types of messaging guarantees or message delivery semantics, and they are at most once, at least once, and exactly once delivery. Let's break down what each of these are and what are the implications of supporting these messaging guarantees. Let's begin our discussion about messaging guarantees with at most once delivery. What at most once delivery means is that the message broker is going to publish a given message no more than once. From the producer perspective, this means that each message is going to be published once, and from the consumer perspective, this means that you also have just one opportunity to consume a given message. If a message is lost from the time that it is published to the time that it reaches the consumer, then it will not be delivered again, which means that we could consume a given message at most once, and in the worst case scenario, not at all. Another implication of at most once delivery is that we have guaranteed uniqueness of consuming messages because they will only be published once. There is also the at least once delivery messaging guarantee, where we accept the reality that messages could be lost, which means that we are going to continue publishing a given message until we have received an acknowledgement from the consumer. So with this messaging guarantee, the delivery of the message is guaranteed, but we could end up producing duplicates. And the last messaging guarantee that I want to mention is exactly once delivery. With this messaging semantics, every message that is published is also going to be consumed, which means that delivery is guaranteed, and we will also never see duplicates, so uniqueness is also guaranteed. The exactly once messaging guarantee is unfortunately impossible in a distributed system, so we are forced to choose between either at most once or at least once delivery. Your choice is going to depend on if you can tolerate message loss or not. Most of the time, you will simply accept the possibility of receiving the same message twice, so you can opt for at least once delivery to at least make sure that you don't lose any messages at the risk of consuming the same message twice. However, there are some techniques that you can apply to implement deduplicating messages from a message broker. And this brings us to the end of the first lesson in our discussion about reliable messaging, where we mainly talked about messaging delivery guarantees. We also reminded ourselves of the fallacies of distributed computing and how they can have an impact on the messaging guarantees inside of an asynchronous messaging system. We discussed the three messaging guarantee levels: at most once, at least once, and exactly once delivery. And in the next lesson, we are going to introduce the outbox pattern into our modular monolith to improve the reliability of our messaging system. Welcome to the next lesson in this chapter, where we are going to implement the outbox pattern. And let's start by explaining what problem the outbox pattern solves using a simplified example. In this code snippet, you can see a use case of creating a new user in our system, inserting that user into the database, and then persisting these changes using the unit of work. We are also publishing an integration event that a new user has been registered using the event pass, and we are only doing this after persisting the changes inside of the database. I explicitly mark the start and the end of the database transaction with comments in the code snippet. The reason for that is that we actually have two transactions in this use case. The first one is the database transaction, where we create a user and then save that user in the database. The second one is our interaction with the event bus to publish our respective integration event. Here is a thought experiment that you can run to see what problem we can encounter with a setup like this. Let's say that the call to unit of work save changes throws an exception. What's going to happen to our system? We are probably going to return an error to the user, but nothing is going to be changed in the state of our system. We won't be saving anything to the database, and we won't be publishing an integration event. Now let's examine another example where the call to unit of work save changes async completes, meaning we complete the original transaction and the user is now stored in the database. But now when we try to publish the integration event using our event bus, this operation throws an exception. And now what we have is our system ending up in an inconsistent state. We have the correct state inside of our database because the transaction has completed successfully, but we are not able to notify the other modules in our system that a new user has been registered because the publish using the event bus threw an exception. And this is the general problem that you can solve using the outbox pattern. If we were to implement our solution like in the code snippet, we could end up publishing the message once, which is the ideal case, but we could also end up not publishing the message at all, which is far from ideal. So the solution that we need is going to allow us to decouple the primary business transaction, which in the previous example was creating a new user and then saving that user in our system, from any secondary side effects that could come out of the business operation that we are executing. In the previous example, that would be publishing the integration event. The solution that we implement should also ensure that our primary transaction is atomic, meaning that either the entire transaction completes successfully or the transaction should revert and we don't make any changes to our system. And this is what the solution for our problem is going to look like when we introduce the outbox pattern. There are two components to our solution, and the first one revolves inside of our unit of work in the command handler. So we are going to start our database transaction and then execute our business logic, which would be creating the user and then storing that inside of our database. Then we are also going to store any side effects as messages inside of an outbox table in the database, and only then we are going to commit the transaction. Because we are only interacting with one external system, our database, we can guarantee that this is going to be an atomic operation. Either everything is going to succeed and we successfully persist both the changes made inside of the command handler and the outbox in the same transaction, or we aren't going to persist anything inside of the database. And then the second component that we need is an outbox processor, which is going to be either a separate process or a background job running inside of our application that's going to fetch any unprocessed messages from the database, and then it's going to process these messages one by one, finally marking each message as processed so that they aren't processed more than once. We should also consider what happens if message processing fails, and in that case we could decide to process the message more than once in the hope that the next time we process a message it's going to succeed. And when you think about it, the outbox pattern is an implementation of at least once message delivery. And now let's jump into the code and I will show you how to implement the outbox pattern inside of a modular monolith. Before we start the outbox pattern implementation, I recommend that you download the latest version of the Evently source code that's going to be available under this video, because I introduced a lot of improvements behind the scenes, like adding more message consumers for integration events between our various modules, and I also added architecture tests for all of the modules in our system. You can go ahead and run the architecture tests to make sure that everything is executing fine, and right now we have 112 architecture tests. If I run them again, you will see that all of the architecture tests that I put in place are passing, and this includes the architecture tests for our entire solution, which is targeting the dependencies between our modules, as well as the architecture tests for individual modules that are enforcing the clean architecture and some other design rules. Now let's go back to the outbox pattern and see how we are going to implement it. Let's consider what we currently have in place in the infrastructure project. If I open up the interceptors folder, you will see that we have the publish domain events interceptor, which is how we are currently publishing the domain events that are raised inside of a single unit of work. So we already have the actual messages that we want to convert into outbox messages. These will be our domain events, except instead of publishing them using Mediator, we are going to store them into an outbox table. So let's start our implementation by introducing an outbox folder into the common infrastructure project. Next, I'm going to add two types inside, both of which you can find under this video. And these types are going to be our outbox message type, which is going to be our main building block for implementing the outbox pattern. It's going to contain an identifier and when the outbox message occurred. It's also going to contain what is the type of this message, as well as the message's content. We are also going to store when this message was processed and if we encountered any error while processing the message. This is going to contain the stack trace of any exception that we run into, which you're going to see when we get to the implementation. We also introduced the outbox message configuration, which is just an EF Core configuration class for the outbox message type. I'm configuring the table where we want to persist our outbox messages using the snake case naming convention. I'm setting up the identifier of the outbox message as the primary key, and I'm also adding a maximum length constraint on the content of the outbox message. If 2000 characters is too little for your use case, given that this is going to contain a serialized JSON document, you should consider increasing this constraint to make sure that you always store the entire content of the outbox message. Now that we introduced the outbox message as a cross-cutting concern, we need to somehow connect it to our database context. So let's take the users module as the example and head over to the infrastructure project, or to be more precise, the users database context. Each of our modules is going to have a dedicated outbox messages table that's going to store the domain events for that particular module, and then we are also going to process the outbox message for each of our modules completely separately from each other. This is how we will continue to keep our modules independent from each other, and we want to persist the outbox message into the user schema in this example. So what I can do is say module builder, apply configuration, and create a new outbox message configuration. This is enough to include the outbox message entity as part of this database context, and now I can go ahead and update my database migration. This is what the updated migration file looks like, and you can see that it now includes the outbox messages table inside of the user's schema, which is very important, and it contains the columns that we define on the outbox type. You can see that the content will be stored as a character varying field of the length 3000, and then you can see the other tables that we already had inside of the users module. I also want to mention that we could make an improvement to this implementation by updating our outbox message configuration and leverage the fact that we are using Postgres. And I could have specified the column type for the content property and set it to JSON or even JSONB. Because the content column in the database is going to contain a JSON string anyhow, we can leverage some capabilities that Postgres has for natively working with JSON types in the database, and we can achieve this if we specify has column type JSON or JSONB. JSONB stands for JSON binary, which is a data type in Postgres that offers some additional features. So because we are using Postgres under the hood, let's go ahead and also specify JSON binary as the type of the content column. If you already applied the migration for the user schema, I suggest that you recreate it to make sure that the content column will have the correct type. So with our outbox messages table in place, the next thing we need to do is to figure out how we are going to store our domain events as outbox messages. And we can go ahead and use the publish domain events interceptor that we already have and repurpose it to now persist the domain events as outbox messages. Another good thing with this interceptor is that it's configured in the infrastructure configuration class, which is going to apply to all of our modules, and we already added it as a database interceptor to all of the database context implementations inside of our individual modules. So what I'm going to do is rename this class and update the implementation, and it's going to apply to all of my database contexts. However, we are going to need to apply the outbox message configuration to all of the database contexts individually and update the respective database migrations for the new interceptor to work correctly in all of the modules. And now let's go ahead and update the publish domain events interceptor. I will start by renaming it into insert outbox messages interceptor. Then I'm going to get rid of the dependency because we won't be needing an iService scope factory anymore. And I'm going to override a different method for the save changes interceptor inside of my insert outbox messages interceptor. And the one that I'm interested in is saving changes async. If you recall from our diagram at the start of